Good evening. Today, we will be discussing the mechanism of electrophilic substitution reaction of aromatic hydrocarbons and the directive influence of a functional group in mono-substituted benzene. We will be exploring how the presence of a functional group can affect the reaction rate of aromatic hydrocarbons. Let's get started. In the slide, it is evident that the mechanism of electrophilic substitution reaction of aromatic hydrocarbons is quite complex. The electrophile is attracted to the atom within the aromatic ring that is of highest electron density. Upon the reaction with electrophile, two species, cationic and anionic, are observed as the products. This is caused by the electron attracting quality of the aromatic ring influencing the course of the substitution reaction. An electrophilic substitution reaction is a common organic reaction whereby an electron-seeking reagent, electrophile, adds to the aromatic ring of an arenium ion to form a carbocation, which is the slow step of the reaction. Afterwards, the carbocation reacts with a nucleophile to complete the process and form the desired product. Through this process, a number of aromatic hydrocarbons can be produced. A proton is removed from a sp2 hybridized carbon atom in the third part of this process. This reaction is initiated by a base, or nucleophile, which abstracts the proton from the carbon atom. This fast step is essential to the electrophilic substitution reaction as a whole. The slide outlines the process of removing a proton from an aromatic hydrocarbon, which is followed immediately by a step that restores the aromatic character of the ring. This process is fundamental to the chemical structure of these hydrocarbons and is integral to comprehending their behavior. When benzene is reacted with methyl chloride in the presence of anhydrous aluminium chloride, the results are toluene, ethylbenzene, isopropylbenzene, and chlorobenzene. This is an example of an organic reaction, which produces a variety of different hydrocarbons. Benzene reacts with chlorine in the presence of aluminum chloride, anhydrous, and forms a series of aromatic hydrocarbons including chlorobenzene, hexachlorobenzene, BHC and dichlorobenzene. These compounds are used in a wide variety of products, from pesticides to pharmaceuticals. Gaining more knowledge of their synthesis helps us to develop a stronger understanding of this important class of compounds. Reaction of benzene to produce benzene sulfonic acid is achieved through sulfonation, which involves the introduction of a sulfonic acid group into benzene. None of the other reactions, bromination, acylation, lead to the production of benzene sulfonic acid. In regards to mono-substituted benzene, it is evident that a functional group has huge effect on its physical and chemical properties. Various functional groups have been proven to modify the structure of the molecule, increase the speed of reaction and affect the reactivity of the molecule. Therefore, it is essential to comprehend the influence of functional groups on the aromatic hydrocarbons to have clear grasp of their function in synthetic processes. We are going to discuss aromatic hydrocarbons, and focus on phenol as an example. We will examine the directive influence of a functional group in the mono-substituted benzene. Substituents that make the ring more reactive than benzene are known as ring activation groups. These groups include NH2, NHR, NR2, O, OR, NHCOR, C6H5, and R. Organic chemists are aware that when certain halogen atoms are integrated into aromatic hydrocarbons, the result is deactivation. In the case that the aromatic hydrocarbons contain ortho- and para-directing groups, these atoms can instead be used to activate them. Knowledge of this process can be applied for multiple purposes, such as for designing pharmaceuticals or creating polymers. Discussing the directive influence of functional groups in monosubstituted benzene and how these groups affect the reactivity of the molecule, we look at examples of deactivating and meta-directing groups, such as nitro, nitrile, carboxylic acid, ester, sulfonate, aldehyde, and alkoxy groups. Taking nitrobenzene as an example, this group has a deactivating effect on the benzene ring, causing it to be less reactive than benzene alone. Aromatic hydrocarbons are a family of organic compounds consisting mainly of carbon and hydrogen. In this particular reaction, one molecule is bromine, bridge 2, while the other is A+ hydrobromic acid, A+ HBr. In order to identify what A is, it must be determined if A is bromine, bridge, bromine OH, bridge O, or both, bridge and bridge O. The answer is both, bridge and bridge O. We observe A, the product of a reaction between chlorine and hydrogen chloride, in this slide. Analyzing the chemical formulas, we can deduce that A is chlorine mononitrite, not NO2Cl. This is the answer indicated by choice A of the multiple choice question. The answer to the question of reactivity amongst the aromatic hydrocarbons is C. IV greater than E greater than I greater than E. Phenol is the most reactive molecule, followed by toluene, benzene and chlorobenzene in that order. This is because the electron-rich hydroxyl group in phenol makes it more prone to attack from an electrophile. There is no doubt that aromatic hydrocarbons pose a risk to our health. Scientific research has confirmed that exposure to these compounds can have damaging effects, both in the short and long term. The dangers range from inhalation and skin contact to more serious illnesses. Therefore, it is important to be aware of the potential risks and take the necessary steps to protect ourselves from harm. Aromatic hydrocarbons are compounds containing certain chemicals, which have been linked to the potential of causing cancer. Research has indicated that long-term exposure to these compounds can increase the risk of cancers such as skin, lung, and bladder cancer to name a few. Furthermore, exposure to these compounds can lead to toxic symptoms, including skin irritation, respiratory issues, and headaches. It is important to understand the health risks associated with these compounds, and try to avoid exposure where possible. Benzene and polycyclic aromatic hydrocarbons are toxic and possess cancer-producing properties. Hydrocarbons containing 2 or more benzene rings fused together are called polycyclic aromatic hydrocarbons. To promote better health, let's now focus on more positive steps we can take in our lives, such as walking for stress relief and improved physical and mental health. Polycyclic aromatic hydrocarbons, PAHs, are among the most toxic substances known. They are created as a result of the incomplete combustion of tobacco, coal and petroleum and can lead to cancer when present in the environment. The carcinogenic effects of PAHs are due to their metabolism in the liver, forming an epoxydiol which reacts with DNA and causes the uncontrolled growth of certain cells. To protect our atmosphere and water sources, it is necessary to take action to prevent the release of these substances. We are examining some carcinogenic hydrocarbons, like 1,2-benzanthracene, 1,2-benzpyrene, and 3-methylcholanthrene. These molecules have the capability to create carcinogenic compounds, and are found in the environment both naturally and industrially. Therefore, it is imperative to comprehend the properties of these molecules and take the necessary precautions when in contact with them. Focusing on 2 specific aromatic hydrocarbons, we examine the structure of 9,10-dimethyl 1,2-benzanthracene, which is composed of 3 benzene rings with 2 of the carbons being methylated. The second hydrocarbon is 1,2,5,6-dibenzanthracene, which is composed of 2 benzene rings with 2 carbons substituted with an alkyl group. These hydrocarbons play an important role in chemical processes and are important to the study of aromatic hydrocarbons. Thank you.